Alright, hey everyone. The goal of this video is to introduce one model selection procedure in particular. And so we've been talking a lot the past few weeks about hypothesis tests for association and multiple regression, other types of hypothesis tests, interactions, confidence intervals, all that type of stuff. Now we're going to change goals a little bit, and for this section of notes, we're going to assume that our goal is just prediction. So we don't really care which variables are associated with the response after accounting for the effects of all the other variables and all that. We just care about predicting the response as accurately as possible when we have a bunch of different candidate predictors. So we're going to jump back to that body fat example. So that was the example that we looked at to investigate multicollinearity. And suppose that we want to predict body fat percentage from these candidate predictors. So there's a total of 15 possible predictors. If you think about all of the possible combinations of those predictors that you could use in a model to predict body fat, including the model that just has an intercept, so that doesn't have any predictors, the total number of different models is actually larger than at least I would think it would be, just kind of looking at it. There could be 32,768 different models. And that's not even including quadratic regression, so including an x squared term. That's not including any interactions. That's just how many different combinations of these can we make to predict body fat. If you had 25 possible predictors, which still isn't that many, then the number of models that you could make jumps up to 33 million. So clearly we don't have time to fit and investigate all of these different models. And so we're going to cover a procedure that will automate the model selection process for us. And that's called best subset selection. And so the goal of best subset selection is that we're eventually going to have R do this. And so we want to fit all the possible models without any higher order term, so without a quadratic or cubic term or anything like that, and without any interactions. And we're just going to choose the best model according to some criterion. And so what is that criterion going to be? Well, there are a few different possibilities, and we're just going to talk about 4. One criterion is adjusted R squared, which we've already seen the definition of what that is. We might fit all of these models and then pick the model with the highest adjusted R squared. Note that we're not picking the model with the highest regular R squared because we noted that R squared is always going to go up as we add more and more predictors, which we don't necessarily want. The remaining 3 are similar to the adjusted R squared in that they're all going to involve a term that rewards good model fit, and then another term that penalizes the number of predictors in our model, because we don't just want a model with millions of predictors. And so Mallows's CP is the first one that we're going to talk about, and we're never going to fit this by hand, but the formula is given here just to kind of point out that we have this part that has to do with model fit, so that has to do with the error terms, and we have this part that is going to act as a penalty for more predictors. And so we're looking for low mallows CP. So we could see that as the number of predictors goes up, that's M, mallows CP is going to get higher, and so that's the penalty for adding more predictors. Another criterion that people use is the AIC, and so we're really not going to talk about what this is because it has likelihood in the definition, and we don't talk about that in this class at all. You'll see that eventually if you take MathStat. But until then, we're just going to note that likelihood is our measure of model fit, and we still have this penalty. So it's really like kind of doing the same type of deal that mallows CP and adjusted R squared is doing. We're looking for low AIC. And we'll just make a note here that this really means like lowest, so not necessarily closest to 0. So if you had an AIC of negative 1,000, that would be better than an AIC of negative 100. BIC looks really similar to AIC. We still have this model fit. We still have this penalty. And BIC, the penalty for adding more predictors is generally more severe than the penalty for AIC. And so again, we're looking for low BIC values. So a model that's good is going to have low BIC. So this take-home message is just that the criterion, any of the 4 that we talked about, is going to do better if the model fits the data better. So it has to do some way with, at least in mallows CP, that's something we directly talked about, the sum of squared error. And each of these adds a penalty for more complex models that include more predictors. Because remember, we don't really want a model with 1,000 predictors if 990 of those predictors aren't really that useful. And so in the next video, we'll get into cross-validation. There are some notes at the end about model selection procedures. I think the most important one is that they're generally not really used as much if we're interested in determining which variables are associated with the response. The model selection for this purpose is kind of like, it's like a little like data snooping a little bit, but we're not really going to get into that yet. We will talk about this idea a little bit more later in the semester. So it's generally just using prediction. Most procedures don't allow us to consider interactions or higher order terms like quadratics, but that is changing as computers get faster and faster. And there's a final note on here that if you have an interaction in your model, then you always generally keep the individual effects as well, which we talked about a little bit when we introduced interactions. Okay, so that's about it for the model selection. You'll see more of best subsets in R.